Passengers in Wuhan are standing on a glass floor looking straight down at streets 20 meters below them, watching the city scroll past beneath their feet while the train they are riding hangs from a single beam above their heads. That train is real. It opened to the public in September 2023, and it is called the Optics Valley Sky Train. But it had to earn the #1 spot on this list, because the competition includes a bullet train that set a world speed record during a passing test where two trains going the same direction created a relative speed of 891 kilometers per hour. There is a train being developed by China's largest missile manufacturer that already hit 623 kilometers per hour on a 2-kilometer test track and has its sights set on 1,000. One train runs on painted lines with no rail at all. One has been carrying commercial passengers at 431 kilometers per hour for over 20 years and still holds the title of fastest passenger rail service on Earth. Today we are going to walk through 7 Chinese trains that together cover more ground than any single country has ever covered in rail technology. Number 7. ART. The Autonomous Rail Rapid Transit, developed by CRRC in Zhuzhou, looks from the outside like someone took a standard articulated city bus and gave it a completely different idea of what it was. 3 connected carriages, streamlined and low to the ground, wide panoramic windows, the kind of exterior you would expect at a modern metro station. Then you look at the road beneath it and there is nothing there. No rail, no groove cut into the asphalt, no overhead wire determining where it goes. The ART navigates using a combination of sensors, cameras, and computer vision that reads lane markings painted onto the road surface, using those markings the way a conventional train uses a rail, as a routing guide, except that, unlike a rail, the markings are just paint. They can be added to any road, changed when needed, and cost a fraction of what buried rail infrastructure demands. The wheels are rubber-tired, which means it rides smoothly on any paved surface and generates significantly less noise than steel on rail systems. The 3-car formation carries up to 300 passengers. Top speed is 70 kilometers per hour. Fully electric, fully autonomous, level 4 driverless operation. The ART was not built as a technology demonstration. It has been deployed in operating transit systems. The city of Yibin in Sichuan province opened a 17-kilometer ART line in 2020. Zhuzhou has its own line. Additional deployments have followed across China, and export discussions have been opened in Southeast Asia, the Middle East, and South America. The pitch to city planners is direct. You get rail capacity transit without the tunneling, without the structural civil works, without the multi-year disruption of installing an underground or elevated system. You paint the road and run the train. The obvious counterargument is that paint can be obscured by weather, debris, or vehicle traffic, which is why the ART sensor suite does not rely on the painted lines as a single point of truth, but uses them as one input among several, cross-referenced in real time with LiDAR and camera data. CRRC has positioned the ART specifically for mid-tier cities that need mass transit capacity but cannot justify full metro construction costs, and that category covers a significant portion of the urban world. The capital cost comparison between an ART line and a metro line is the detail that makes city planners take the meeting. A conventional underground metro line in China costs somewhere between 500 million and 1 billion yuan per kilometer to build, accounting for tunneling, stations, civil works, and systems installation. An ART line on existing road infrastructure costs a fraction of that, with the primary expenditures being the vehicles themselves. From a train that needs no rail at all, we move to the one that built China's reputation for high-speed rail in the first place. Number 6. CR400AF Fuxing. In June 2017, a train called the Fuxing, which translates to rejuvenation, entered service on the Beijing-Shanghai corridor. It was not China's first high-speed train, but it was the first one built entirely from Chinese engineering rather than licensed foreign technology. And the number it posted as its commercial operating speed changed the global conversation about what a regularly scheduled passenger train could do. 350 kilometers per hour. Not a test speed, not a one-time record run. the routine operating speed at which passengers board, ride, and step off onto a platform on a daily basis, across one of the busiest rail corridors in the world. The Shinkansen in Japan, the ICE in Germany, the TGV in France, all operate their fastest commercial services at between 300 and 320 kilometers per hour. The CR400AF runs 30 to 50 kilometers per hour faster than any of them as its standard. The train itself is 440 meters long in its full 17-car configuration, seats over 1,283 passengers, and is equipped with more than 2,500 sensors monitoring everything from axle temperature to pantograph contact pressure in real time. The aerodynamic nose stretches 15 meters and was designed through more than 5,000 computational fluid dynamic simulations to reduce drag to the level required for sustained high-speed operation without excessive energy consumption. The ride inside at 350 kilometers per hour is smooth enough that a coin stood on its edge on a table will stay standing, a test the operators have done publicly and repeatedly. China's high-speed rail network, which the CR400AF operates across, now spans more than 46,000 kilometers, more than the rest of the world's high-speed rail networks combined. Every day, millions of people board Fuxing trains without giving the 350 kilometers per hour beneath their feet a second thought, which is the most persuasive argument possible that high-speed rail at this level has stopped being extraordinary and become ordinary. The scale of China's high-speed network built around the CR400AF is the other number that deserves attention alongside the speed. The CR400AF does not just run fast. It runs fast across a network so large that the entire high-speed rail infrastructure of every other country in the world added together is still smaller than what China built in under 3 decades. From the train that set the standard, we move to the one that is about to raise it again. Number 5. CR450AF and CR450BF. On December 29, 2024, CRRC held a press conference in Beijing and rolled out 2 prototype trains side by side. The CR450AF, designed by CRRC Sifang in Qingdao. The CR450BF, designed by CRRC Changchun. Same family, 2 different builders competing on the same track toward the same goal. Both are engineered for a commercial operating speed of 400 kilometers per hour, 50 faster than the Fuxing, and a design ceiling of 450. During test runs that year, the CR450AF hit 453 kilometers per hour on its own and was part of a 2-train passing test where the combined relative speed between the 2 approaching trains reached 891 kilometers per hour, a world record for any conventionally wheeled train. Getting a train to go faster is not simply a matter of more power. At speeds above 350 kilometers per hour, aerodynamic drag scales with the square of velocity, which means even small speed increases demand disproportionately larger energy inputs unless the aerodynamics are fundamentally redesigned. The CR450 addresses this by cutting total running resistance by 22% compared to the CR400, achieved through a redesigned bogie system, revised pantograph geometry, and a front nose profile refined through more than 3,000 computational simulations. The train is 10% lighter than its predecessor through greater use of aluminum, carbon fiber, and glass fiber composites, and the traction system switches to water-cooled permanent magnet motors that consume 20% less energy at high speed. Over 4,000 onboard sensors monitor the car body, bogie, pantograph, train control, and fire systems in real time, and an over-the-horizon detection system provides early warning for obstructions beyond visual range at operational speeds. Passenger space expands by 4%. Interior noise drops by 2 decibels. The braking distance from 450 kilometers per hour matches the CR400's stopping distance from 350, which is the engineering detail that signals real maturity in the design. The CR450AF is expected to enter service on the Beijing-Shanghai line in 2026 and on the new Chengdu-Chongqing line in 2027, where the 400 kilometers per hour operating speed will cut the travel time between those 2 cities to under 50 minutes. Number 4. Shanghai Maglev. In 2004, while most of the world was still treating magnetic levitation as a research concept with a promising future, Shanghai opened the world's first high-speed commercial maglev service. The line runs 30 kilometers between Pudong International Airport and Longyang Road Metro Station in the east of the city, and it covers that distance in 7 minutes and 20 seconds. A taxi between the same 2 points takes between 30 and 60 minutes depending on traffic. The maglev charges 50 yuan for a single journey, and the math of time versus cost is the reason the line has operated continuously for over 2 decades. The technology is German. The Transrapid system was developed by a consortium of German companies across several decades of research and pilot projects, and China licensed it for this line after German domestic politics repeatedly blocked construction of commercial Transrapid routes in Germany itself. The irony is that the most visible and commercially successful implementation of German maglev engineering is in Shanghai, not in Germany, and has been for 20 years. The operational speed the service runs at is 431 kilometers per hour. That is the standard running speed for this line on a regular schedule. The record achieved during testing was 501 kilometers per hour. At 431, the train is traveling faster than any other passenger rail service in commercial operation anywhere in the world, which is a title it has held without interruption since the line opened. The physics of how it achieves that speed matters. Maglev trains have no contact between the vehicle and the guideway. Electromagnetic forces from coils embedded in the guideway lift the train approximately 10 millimeters above the surface and propel it forward. Without wheel-on-rail contact, there is no mechanical friction, no wheel wear, no rail wear, and the primary resistance to motion is aerodynamic drag. That absence of contact also means the Shanghai Maglev operates virtually silently at the platform level. The line extension to Hongqiao Airport, which would bring the total route to 47 kilometers and connect both of Shanghai's major airports in a single maglev journey, has been discussed, planned, and replanned for years. Whether it happens depends on questions of cost and urban planning rather than engineering. The engineering was settled in 2004. The passenger count the Shanghai Maglev has accumulated since 2004 is in the hundreds of millions. The trains have completed millions of service runs. The engineering has proven itself not in a controlled test environment over a few months, but in daily commercial operation over 2 decades of weather, passenger loads, and infrastructure wear. From the maglev line that has been running commercially for 20 years, we move to the one China is building to make that look like a starting point. Number 3. CRRC 600 km per hour maglev prototype. The Shanghai Maglev uses German Transrapid technology. The 600 km per hour prototype that CRRC unveiled in Qingdao in July 2021 is entirely Chinese, developed through a program under China's 14th five-year plan that set domestic high-speed maglev capability as a strategic engineering priority. The vehicle on the platform in Qingdao was not a scale model or a concept render. It was a full-size train body, ready for track testing, built on an electromagnetic suspension architecture that lifts the vehicle without any contact with the guideway using onboard superconducting magnets rather than the powered guideway coils of the Transrapid system. The design speed is 600 kilometers per hour. At that speed, the journey between Shanghai and Beijing, which takes around 5.5 hours by high-speed rail today, would take approximately 1 hour and 40 minutes. The same distance by the fastest available commercial flight takes around 2 hours and 15 minutes from airport door to gate, without accounting for check-in and security. A 600 km/h ground-level maglev train competing directly with domestic air travel on time from city center to city center is the strategic proposition that has driven the investment. The test facility where active trials are being conducted is in Datong in Shaanxi province, where a dedicated high-speed maglev track has been built specifically for the program. Speed results from those trials have not been publicly released with the detail that the T-Flight program releases. The three-carriage configuration shown in Qingdao has a streamlined profile that substantially extends the nose length relative to earlier Chinese maglev designs, addressing the aerodynamic challenge of pushing a blunt-fronted vehicle through air at speeds where drag is the dominant engineering constraint. A Chinese-built maglev operating at 600 km/h would not just add a fast train to the network. It would make the majority of domestic Chinese air routes commercially uncompetitive on journey time while running on electricity from the grid rather than jet fuel. The geopolitical dimension of building domestic maglev capability rather than continuing to depend on licensed German technology is also worth naming. The Shanghai Maglev demonstrates that maglev works commercially at scale, but it also means China's highest-speed commercial rail service runs on a technology platform it does not own and cannot independently upgrade or expand. The 600 km/h domestic program is the answer to that dependency, and the Qingdao unveiling was as much a statement about technological sovereignty as it was a demonstration of engineering capability. From a production track maglev chasing 600, we move to the one that has already gone faster than that and is treating 600 as a speed it passed on the way to somewhere else. Number 2. T-Flight. The China Aerospace Science and Industry Corporation, CASIC, is China's largest manufacturer of strategic and tactical missiles. It builds ballistic missiles, cruise missiles, air defense systems, and anti-satellite weapons. It is also, since approximately 2017, building a hyperloop. The T-Flight is the result, and the reason a missile company is developing a vacuum tube maglev train is straightforward once you understand the engineering overlap. The core challenge of the T-Flight is managing the behavior of a vehicle moving at extreme speed inside a sealed tube, including the pressure dynamics, the structural loads, the electromagnetic fields, and the control systems that keep the vehicle stable at velocities where any deviation from the design parameters becomes catastrophic very quickly. These are problems that a missile manufacturer thinks about from a different angle than a railway engineering company, and CASIC's background in high-speed projectile dynamics, sealed tube flow management, and precise electromagnetic guidance turned out to be directly applicable. The test facility in Shaanxi province contains a section of sealed vacuum tube 2 kilometers long with an interior diameter of 6 meters. The track inside is machined to a flatness tolerance of 0.3 millimeters across its entire length. In February 2024, on that 2-kilometer track with the tube pumped down to low vacuum conditions, the T-Flight reached 623 kilometers per hour. That speed broke the previous world record for a superconducting maglev vehicle, which had been held by Japan's L0 series at 603 kilometers per hour. Though Japan achieved that number on a longer conventional test track rather than a vacuum tube. By October 2024, CASIC confirmed successful testing under active low vacuum conditions, validating that the pressure management systems, the vehicle control, and the levitation all performed to specifications simultaneously in the operating environment the production system would use. 2 kilometers is extremely short for high-speed testing. The Shaanxi track was built as a proof of concept. The second phase calls for a 60-kilometer track that would allow the T-Flight to approach its intermediate target speed of 1,000 kilometers per hour. The ultimate roadmap targets 2,000 kilometers per hour, which would be Mach 1.6, faster than a supersonic military jet in cruise. Virgin Hyperloop, the best-funded Western equivalent, burned through $450 million and shut down in 2023 without carrying a single passenger. CASIC has completed something none of the Western Hyperloop companies managed, a full-scale vehicle test under actual low-vacuum operating conditions at a speed that broke a world record. Number 1. Optics Valley Skytrain. Every other vehicle on this list moves along a surface, whether that surface is a painted road, a steel rail, an electromagnetic guideway, or the interior of a vacuum tube. The Skytrain in Wuhan does something that sounds like a grammatical error the first time someone describes it to you. It hangs beneath its track and flies through the air with the city visible in 3 directions, including directly underfoot. The formal name is the Optics Valley Suspended Monorail, and the Wuhan government calls it the Optics Valley Photon. Photographs and video of it taken from street level produced a genuine moment of public confusion when they circulated online in 2023. It is the first suspended monorail in China, which in a country that has built more rail infrastructure than the rest of the world combined over the past 20 years, is a meaningful distinction. The line opened on September 26, 2023, runs 10.5 kilometers through the Optics Valley Ecological Corridor, connecting Jufengshan National Forest Park to Longquanshan, serves 6 stations, and operates trains every 10 minutes from 8 in the morning to 8 at night. The vehicle configuration is flexible, running between 2 and 6 carriages depending on demand, with each carriage accommodating up to 200 passengers. The structural logic of a suspended monorail is counterintuitive but efficient. Because the vehicle hangs below the beam rather than sitting on top of it, the center of gravity sits naturally below the point of contact, which gives the system an inherent pendular stability that top-mounted rail systems require engineering effort to achieve. The beam itself can be narrower and lighter than a conventional elevated rail because it carries load in a different way, and because the vehicle does not need to balance on top of it. The result is an elevated transit system that has a significantly smaller visual footprint and a lower structural cost than a conventional elevated metro line. The carriages are equipped with side windows that open 270 degrees and a transparent floor panel running through the passenger cabin. What this means in practice is that someone standing in the aisle of the SkyTrain looks down through the floor and watches the parks, roads, and neighborhoods of Wuhan pass beneath their feet with nothing between them and the view. The exterior design was given the name Wings of Technology and finished in what Wuhan's transit authority calls Technology Blue, a deliberate visual identity decision for a line that runs through one of China's most concentrated technology development zones. The fiber optic monitoring system embedded along the track beam measures temperature, vibration, and structural stress in real time and flags anomalies before they become operational issues. Operation is fully driverless, level GO A3 automation. The line currently carries around 13,000 passengers daily, a number that reflects its current status as both a transit service and a tourist attraction. Phase 2 of the line would extend it to 26.7 kilometers with 16 stations total, which would convert it from a tourist highlight into a full transit artery for the district. This is the train that earns the top spot not because it is the fastest or the most technologically extreme, but because it produced a moment that none of the others could. It made people stop scrolling, look at a photograph, and genuinely not understand what they were seeing for a few seconds. It made a train feel like something new.